What we're going to do is we're going to look at functional groups, which are a group of atoms that are attached to our carbon chain. And what we do is we replace our hydrogens that are on the carbon chain with other molecules. And the reason that we're interested in doing this is because they can give our organic compound different chemical and physical properties. So if we know what functional groups are attached to a molecule, we can make predictions as to what reactions it will undergo, and also we can make predictions based on its properties. So we're going to look at a variety of them. For here are examples of 3 of them, in which I replaced the hydrogen on my carbon chains with other things. Now, one of the things that I just want to point out here is we often will use R to denote a carbon chain of any length or unknown length. And so here I would have a carbon chain of some length, and attached to one end I would have an OH group, and we would call that a alcohol. And we have aldehydes and carboxylic acids as well. Okay. Now, the first type that we're going to look at is what we call organic halides. And an organic halide, I take one of my hydrogens from my carbon chain and I replace it with a halogen. Okay. Now, my halogens can attach to my carbon chain at any point, but when we name them only in prefix, and we have to state their location. Now, before, when we were talking about priority and we were looking at numbering of the chain, we said that the highest priority thing gets named first. My alkyl halides have a lower priority than double bonds. And double bonds have a lower priority than triple bonds. So, for example, if I had a carbon chain with fluorine attached to it, I'd use the prefix fluoral. If I had a carbon chain with chlorine, prefix chloral, bromine, bromo, iodine, iodo. So, for example, here I have a carbon chain, and just like we learned to name before, the first thing I do is identify my longest chain. And I see that it's 2 carbons long, so it tells me that my root is eth, and it has only a single bond, so therefore it's going to be an ethane. And now I have 2 chlorines attached to it, so we know that we name chlorine with a prefix of chloral. Because there's 2 of them, it'll be a dichloral, and now we have to state the location. And so because there's no preference as to what end I start at, it'll be a 1, 2. And so now what I need to do is just need to put all of the name together. So 1, 2, remember comma between numbers, dash between numbers and words, dichloral, ethane. Okay, when we go to draw them, again, we take into account the same thing. So here I have 1, 2 dichloral, 1, 1, 2, 2 tetrafluoral ethane. So we know from our name, right, we can see our root is 2 carbons long, and from our suffix we can see that they are joined together with a single bond. So therefore what I'm going to do is I'm going to put my 2 carbons, and I'm going to join them with a single bond. Then now I know on carbon 1, I'll call this one carbon 1, I have a chlorine. And on carbon 2, I have a chlorine. And then on carbon 1, I have 2 fluorines. And on carbon 2, I have 2 fluorines. Okay. And then I would go and just make sure that each of my carbons have 4 bonds. So 1, 2, 3, 4, 1, 2, 3, 4. So I don't need to add any hydrogens. Okay, so here if we want to name this as well, what we recognize is, first of all, this would be my root. And we recognize that this is what we call our benzene ring. So therefore my root for this is benzene. And now I have 2 chlorines attached to it. So again, it would be a dichloral. And it doesn't matter which way I count. I can call this chlorine carbon 1, in which case I would count that way. Or I can call this carbon 1, and I could count that way. But at any rate, it would be 1, 2, dichloral, benzene. Okay, now my alkyl halides can be involved in a number of reactions. First of all, our preparation, as we've already talked about, they can be made through two types of reactions. The first reaction type that they can be made through is through an addition reaction, and this is where we add an halogen or a hydrohalide to an alkene or an alkyne, as we've just talked about in another video. Or we can do it through substitution. In this case, I take my alkane and I replace one of the hydrogens with a halogen. Okay. Now, another reaction that they can be involved in is to make other groups. And so the one that we're going to look at today is elimination. This is where my alkyl halide could have the halogen removed. And so the carbon that has a halogen will lose it, and one of the carbons on either side will lose a hydrogen to allow for a double or triple bond to form. And this gives me my alkene. And this is one of the ways that we get alkenes. So for example, here's our reaction, and I have my two carbons that have their halogens. One has a halogen, one has a hydrogen, and they'll undergo a reaction with a hydroxide ion, and this will give me my alkene, water, and a halogen ion. Now, when we have a reaction occur with an unbalanced alkyl halide. So for example, this carbon here has my halogen. And so I know that this carbon is going to lose its halogen. And as a result, a hydrogen from one of the carbons on either side could be lost. So I could lose this hydrogen, or I could lose this hydrogen. And so this means that I have two possible products. Now, just like we had our Markovnikov's rule, we have a rule for when we do elimination reactions as well to make a prediction as to my most likely product. And it says that the hydrogen poor carbon is more likely to lose its hydrogen. So therefore, if we look at this carbon has only two hydrogens, whereas this carbon here has three. So as a result, when we get our two products, I'm more likely to have this as my primary product and have the carbon on the end keeping its hydrogen and the carbon that had two hydrogens lose one. So this would be my major product, but I would still get some of the other product formed.